So today's Voyages prac is about speech synthesis and text-to-speech. Begin by giving respects to the traditional owners of the lands where I am, Gubbi people, and the Turrbal and Yagara people of Meander in Brisbane, where University of Queensland is. So today we're going to be looking at speech synthesis and using some collabs. The steps that we'll go through are on that Voyages site. I'll drop the link into the chat. And the assessment material is on Blackboard as well. And the updated criteria sheet is here in the chat also. So what we'll do today is go through a few speech processing techniques and look at some text-to-speech, speech synthesis, some speech generators. And at some of these points there'll be output that we'll save to upload to the assessment item. So it might be worth having a look through that assessment criteria sheet. It will identify when to save files and at what points to think about the different techniques that we're looking at. So the links are on that Voyages page as well. The first thing, we'll use Audacity, which is a sound editing program. So grab the link, go there and download it if you haven't got it already. I think we should all have it from the previous weeks, is that right? Let me know if you need time to download it, otherwise we'll just keep going through. And here we can either make a new recording of your student number, or you can use one from the previous weeks and save that as a WAV file, and then we'll open that up in Audacity. So this is mine. This is a mono file, single channel. And there's down the bottom left of the screen, we can see that it's 44.1 kilohertz, 44,100 hertz. It's only a short file, 4 seconds, 4 and a bit seconds long. So we can open up your student number file. What would you do is to process the file to first change the pitch, and then we'll change speed and change tempo. So these are some of those techniques that David talked about in the lecture of altering the sound files. Different reasons for doing that, maybe can augment a training data set by pitch shifting some source material. We can sort of make a system more robust for generalization. We can record some material and then pitch shift to get versions of that at a higher pitch or a lower pitch. And one of the things that Audacity can do is to change the duration of the file, either by changing the pitch or by re-tempoing so that the pitch stays the same. So first have a listen to it, and then you can either select an area, or if you leave it unselected, it should process the whole file. And so in the effect menu, we have many options for doing sound distortions and reverse the file. Good fun. So here, the first thing we'll do is to change pitch. So we choose this from the menu and have a play around with adjusting the percentage change. You can either click OK, it will process, or you can click the preview. Get some chipmunks sort of things happening. So it doesn't take much to affect it. It's like helium voice. Okay, so you can choose to perform this at high quality. Select this. You can try to auto tune using this the key values here. So click out. So make some either a positive or a negative change. Click OK, and then we can save that. Now, Audacity is slightly different from some of the other audio programs in that saving a project is different from saving the audio file. So the project itself does have the audio data in it, but it has all this other stuff. It's kind of a strange file format. So rather than just saving the project, we want to export as WAV. And I'll save this as student number 1. It'd be good if you can include your actual student number on there, like whatever. There's no need to add the metadata tags. You can skip that. Okay, so once we've saved or we've exported that, we want to revert, or you could either undo. So go back to the original recording. And then we'll do the same with change speed and change tempo. So when we do the change speed, we'll see that the duration of the file is affected. We're also changing the pitch. So if we're changing the speed, making it shorter, it will increase the pitch. If we do it by lengthening the file, we decrease the pitch. Hadn't noticed this before. It looks has a handy setting to speed up or to change the speed of the vinyl rip. So this could be useful if you're digitizing records. You play them at 78 and then convert them to 33 1/3. Would make the digitization process quicker. So as you go through, save the change speed as version 2 of that file, and then change the tempo and save that as version 3. so that you can hear the difference with the tempo. It does change the duration, but it keeps the pitch the same. So it does this by resampling and inserting, by changing the dynamics of the waveforms. Okay, how's that? So now I'll download some audio files. We'll use these to do some normalization in Audacity again. So this the link. Put that in the Zoom chat. From this folder of audio, I'll download the one called Kicking You're Very Quiet. I'll download them all and do a comparison. Some I prepared earlier. So I'll open this up in Audacity. This is a recording. Must be done now. Some information in the README file there about where this recording came from. It's a public domain, recorded in 1941. Recording of some songs. The reason I'm using this is that it's open. It's like public domain, means that I can use it without copyright concerns. So it's an alternative to Creative Commons. All right, great. For banjo. Friday afternoon banjo session. So this is the original recording. It's not particularly high. The frequency, or the waveforms are not particularly well distributed in any case. So there's a limited range in the recording. If I was to open up this very quiet one, you can see that the waveform of the very quiet version is even much more reduced. So there's very little dynamic range in the waveform. If I zoom in, use this magnifying glass tool to zoom in, we can look at the waveforms of both of them. The original one does have a little bit more height in, whereas the quiet version, it's almost imperceptible. The waveform just has there's no range. So normalization is a audio processing technique whereby the audio is the amplitude is increased to maximize the volume either across the whole track or in different sections. go back to using the cursor. So here I'll choose just a section and go to Effect, Normalize. And I can normalize to a peak. So if that was normalized to 0, it would try to maximize the change in the volume and the amplitude of the signal. Or sometimes it's safest to just do it a little bit lower than maximum. So there we go. We can see now that it's been normalized. It's going to be a lot louder. So just be careful. I'll play the original one. Excuse me. And then I'll play the normalized version, and we'll hear a significant difference. It's still too loud, so just turn the volume down from that. So this technique is useful, especially with field recordings where the microphone might be placed a long way away from, or at some distance from the sound source. We can process the signal and try to boost the volume of the signal, and then that's going to give us much better material to work with in our language tech. Savita didn't hear the audio. Did you hear the? Oh, it might be. Maybe it's not playing through on the Zoom. Do you hear any of these?
When you were playing the other one in the loud bit, then it sounded kind of like it was from like 2 rooms away, sort of.
Oh yeah. Okay, so the loud bit. So in this section that I've got highlighted here, the loud bit is the bit that I've normalized, and then the bit that you probably can't hear is because it's so quiet. So do you get that effect when you do it yourselves?
Yeah, I think it's possible it might just be something in the Zoom settings about which audio it's picking up.
Yeah, maybe. Okay, so again, for the assessment, save the normalized version of that. And we'll upload that into the Blackboard. There's another file in that folder. If you're interested, this one is not so much for assessment, but just as a comparison of what happens when we're working with a stereo audio file. In this case, it happens to have 2 speakers. So one channel is one speaker, the other channel is the other speaker. The speaker separated. And then you can see just a quick visual on the waveform shows us, we can see that one of the channels is, so the top channel appears to be louder, or the waveforms cover a greater range than the bottom channel. So if we were to normalize across both of those channels combined, then it will normalize to the maximum on the loudest channel. So it'll make the loudest channel louder. It'll make the quieter channel loud by the same amount. And so in these sort of situations, it can be best to normalize a channel at a time. So that's one that you can play with for your own interest. And that audio file comes from a different data set of air traffic control, which this is the page about it. I think that's linked in the document. So this data set is often used for developing language tech, speech recognition. It's particular because it has these multiple speakers. It's quite noisy, although there's quite a kind of contained vocabulary in what they're talking about. So it sort of limits the problem of developing a general system. And there's also quite a bit of speaking over the top. So although they're on separate channels, people can test the development of speech recognition systems that can try to identify or separate speakers where there's overlap. Okay, any questions about those processes? Did it all work okay? Does anybody want to share their pitch shifted? You could do a screen share and play it. And I'll have a laugh. Okay, so we're still on waveforms and things. This is a collab that we can use to generate waveforms, visualizations of the waveforms, and generate spectrograms and MFCCs. So there was some questions in the lecture about different types of feature extraction. So here's some techniques for doing it. Nice one, Lucinda. That's crazy. I wonder what would happen if you pitch shifted deep and then compressed it and then pitch shifted deep again. Okay, so this collab, it's linked in on the Voyages site. This one not for assessment, more of a interest thing. So we'll start. I think this one doesn't need a GPU. So begin by installing this PySound file package, and then we'll import the packages that we're going to use in the examples, and and we'll download this audio file, which I've put up on this website as a convenient place to get it from. So that should end up in excuse me, in the files area. Now we can use the sound file package and Librosa to plot the waveform of that audio. I'll play it.
Amakan di kaya ramila. Amakan di kaya ramila.
And there's our representation of it in the waveform. So this is not interactive. We can't zoom in and out of it, but we can see how it's represented as a wave. We can generate a spectrogram again using the browser, and let's see. So there's different representation of the frequency over time. Showing similar sort of data as the waveform, but there's a lot richer in that we also getting a decibel, like the intensity of the air pressure of the sound is represented as well. So it's like a three-dimensional representation of the sound file, whereas this one is amplitude over time. There's no indication of the strength of the signal. The spectrogram, the colors represent the strength. And we can also generate the MFCCs. And here's the plot of the MFCCs. That one. Okay, so the MFCC plot is also reducing. It's only giving us up to, looks like about 11,000 hertz. So it's dropping off the top part of that, what we're seeing in the spectrogram. So a reduced amount of information. That's particularly useful for speech, for human speech. And there's also a link there, which is a serious textbook for, the link doesn't work, great. So this is a textbook, an online textbook currently in production, which covers a lot of language tech. It's worth looking at in different parts of this course, particularly there's the chatbots and the discourse section will be relevant in a couple of weeks. But this chapter 25 has the information about phonetics, and the chapter 26, the ASR and TDS, go into much more detail about these techniques. So I'll just, for quick interest's sake, skip down to here. We won't go through this right now, but if you're interested in how these MFCCs are generated and what they're representing in more detail, then this is quite a good description of how we go from waveforms, what are the waveforms representing, and then how these MEL frequencies are calculated, and then also what they represent. So it's quite detailed. There's all the math there if you're interested in that. So representing a particular waveform in a spectrographic representation of it, and then using that to generate these more complex, or to understand these more complex spectrograms. So one of the things about these spectrograms is that they can be read and you can interpret these key frequencies across the sound file. So we won't go into that level of detail in this course, but there's some links into the deeper detail if you're interested. So feel free to also, you could try uploading your student number into that and change the links in there. Just drag and drop it, because it's so small, it's not going to be significant. If the color restarts, it won't be too hard to drop it in again. So if I've dropped that into the file, I can update that web. I might just make a new one. So make a new code cell so that I can run that without re-importing everything. So the audio file reference to my web, and then regenerate the waveform. You can see the representations very clearly, these clearer enunciations of things, but there's also these leading transition sounds.
4, 5, 6, 8, 7, 3, 9.
Oh, great, that's the fast one. What's the spectrogram look like for that? The MFCC. So you can see the MFCCs quite clearly, these different spoken groups. Okay, so let's have a look at some TTS systems. We'll look at what, four different techniques, or three main ones, and then a voice clone. So the first one is very crude. It's a super basic concatenative system, and so this is by far, this is far from state of the art. So as David said, it's these kind of things these days are useful only to test your pronunciation lexicons, but they're also kind of interesting just to see where this has moved, or how it's developed in the last couple of years. Get it running first. It's going to download a repository which has some pretty basic Python code and a bunch of audio files in it. Start doing that. It shouldn't take too long. So we download the repo, unpacks the WAV files, installs some stuff. So it should be good to go. So now we're checking the content files. We've got sent me there. So the masters.zip is the file that downloaded and was unpacked into Cmu. There should be in the data folder in Voices. We have a bunch of audio files. You can double click on them and listen to them. There's separate sort of phone sequences. Pronunciation.csv is a list of words and some representations of the phones that are used to create that word. So let's have a look at the word like. 27. If I was to look at the number 27, that listen to that, it'll be the sound l, the 12 will be I, and then 26 will be k. Yeah. So it gives you an idea of when David was talking about concatenative systems are pretty bad. They really are bad. So you can change the message there and see what it, see how it goes. Probably put that into a separate cell as well.
My name is Ben.
Now, yeah, really bad.
My name is Ben.
So the last code cell here is just a method of listening to individual files rather than downloading them if you wanted to try that. So if you listen to some individual files, it will give you an idea of whether they're see if you can tell whether they're phones or diphones or triphones.
Now.
And that might be a clue as to why it sounds so ransomy. Okay, so after you've done that, save a copy of the collab in your drive and make sure the sharing is enabled. Keep the link, and we'll need to submit the link to the collab with those files generated so that we can check it. So one way to improve this one might be to increase the number of phones and then boost the pronunciation dictionary. So the pronunciation dictionary, oh, I was just looking at that a moment ago. If we added more instances of words in here, then it might have a better chance of, so if we use bigger tokens or bigger units, so rather than each phone unit, we could go to diphone, triphone, or even word units. So if we had a recording of the word name, then we could include that as a separate audio file in the Voices data. The pronunciation dictionary could have the word name instead of being composed of these 3 separate phone sounds, each of which is represented by an individual audio file. If there was a single audio file of the word name being spoken, we could just put the reference to that there. So it is a technique that some people still use. The benefits of it is it's super quick, easy to put together. Doesn't take a lot of data to make a system, so you can make a very crude system with 40 sound files. So it's a place to start. So the next one we're going to look at is deep voice. So this is a much it's a more sophisticated technique. This one's still from a couple of years ago, so we're going to use an older version of TensorFlow, just because the Colab was written for a certain sort of dependency set, and maybe one day we might update that for the demo, but it works just fine with the old packages. So in this one, we're going to specify the TensorFlow version. So Colab these days will, I think, uses TensorFlow 2 by default. So because this project needs older code, we start by setting the TensorFlow version here. This one, we do need to be on the GPU. So change the runtime type if you need to. Make sure when you're saving the copy as, change the omit code cell output setting, so that when you do run it, your code cells, the output of your code cells will be visible by us when we come to have a look at them. So this comes from again, that's a Git repo. Yeah, a few years ago, still works. It's kind of still a good demonstration. So we're going to look at the single speaker demo. So got the machine going. There were a couple of changes that I had to make this morning to just so that it ran, because it is a bit old. So we set TensorFlow version 1. Don't think I need to do that, but I might as well anyway. And now we clone the Deep Voice PyTorch project. We're using a fork of the original, because I had to pin a couple of, or unpin a few dependencies that were conflicting version numbers. So that's cloned here in the Deep Voice 3 folder. And we're going to change into our working directory here and install the packages that this thing needs. So this line is a legacy from the original, which the working version was on some old commit. We've avoided having to do that because we're checking out the branch up here, rather than checking out master and then, rather than cloning master and checking out the commit, we're cloning the branch that has the updates on it. All right, so there's some error messages here, but I think it is going to run in spite of those mismatches. If anybody feels like updating or conforming all of those package versions, most welcome. So here we're going to install libbrowser again and NLTK. So libbrowser is the package for analyzing audio files. NLTK is the handy NLP tool. And we're going to download this Cmu Dict data. So Cmu Dict, the Carnegie Mellon University Cmu Dictionary. The link was not working the other day when we were in the lecture, but I'll see if it's active today. The GitHub link works in the Zoom chat. So this is the data. I'll just zoom in a bit so we can see it. So Cmu Dictionary is an English, well, it's an American English dataset. And it breaks words down into these pronunciation lexicon. So the symbols that it's using are alphabet, an ASCII table. So rather than IPA, it's an ASCII dataset, and all of the sounds that are represented by combinations of letters and numbers. So it's a fun thing to look through and see how these sounds are used. So heel, heel, some kind of curious words in the midst of all of this as well. Hog, hog, maybe not how we might say it in Australia. I'm lucky to even say hog in Australia. Okay, so the Cmu Dict will be downloaded, and then we're also going to download some pre-trained models. So these are the deep voice models. Rather than go through the process of training deep voice on a data set, we're going to use the the pre-trained one because it's quicker. And so this file that we're downloading is a parameters. These are the parameters for the model. So if you were training, there'd be some of these you could adapt based on the data that you were working with. So they've downloaded, and now we can set up the parameters for the system. And these functions it'll help us for the Colab, so that when we're actually doing our generation, we can call these helper functions. So now we can load our model, load the pre-trained model. And then we can put some sentences in here. So this is an array or a list of multiple sentences. Feel free to change these however you like. So we'll press play on that cell and it'll generate audio players with TGS synthesized from those sentences.
The surcounters noted the modern world. The nautical boy means a late segment. An empirical reformer provides a concrete met.
So what do we notice about the difference between these and, say, old Edward back there?
The surcounters noted the modern world.
Certainly a lot more intelligible than the concatenative approach, and it's also a lot more human-like. Still got this kind of shimmering effect on it. Yeah, there's stress. So there's across those utterances, there's the stress or the intonation, the flow across the utterances. It's much more than on anything in a concatenative approach will just be a remnant or a legacy of the training data. This link that I've just dropped in the chat is one of these sentence data sets. So if you're having trouble thinking of sentences yourself, this is a bank of sentences that make a little bit of sense. So David introduced us to a couple of different data sets. There's these Harvard sentences, and there's the SUS and the NIT data sets. The SUS one, the SAS, there's a collab there that you can use to generate sentences, and then the NIT one, this is the semantically unpredictable. Again, it's another version of the SUS one. So nice to try this with other nonsense sentences and see how it deals with it.
The lucrative cooperatives swim the triangular coaster.
So we can represent this this devoice 3 collab has some built-in visualizations as well, so we can see the MFCCs of it. And if you wanted to, you could copy the librosa stuff out from the other collab and have a go at representing the MFCCs of the signal as well. As you can see in here, the formant bands, so the shimmeringness of this system, you can clearly see that the sort of waviness in the in the generated speech is visible in the spectrogram. And so there are some techniques that people use to smooth that out. There's a couple of links on the site with some more information about Deep Voice 3, some more information about the model architecture and such. I'll just drop that here for a quick visual reference. So yeah, this is what 2017, where we started to get some more natural sounding synthesis. So more information about the model architecture in that, if you're interested. And there's the link on the collab is back to the original where this collab was published. Okay, so for the assessment, run that. Or save a copy of the collab, run it, change some of the sentences, and then generate those plots. And we won't cover this attention plot, but look at the spectrogram and just sort of maybe describe something about the spectrogram that you notice, how it correlates with the sounds that have been generated. It might be about that shimmering, the waviness of the strength of the signal. You can see it's also still quite hard edges in between some of the sounds, maybe more so than if it was a natural voice. So these, well, we listen to the sound, that gives us a really great way to evaluate the naturalness and the intelligibility. We can also use these visual representations as an assessment. How did that go? Everyone at work fine? Any problems installing? All right, so here we have Tacotron 2. So this is the technique whereby the audio is generated from the spectrograms. So there are a couple of parts to the system. There's a very high level view of the architecture that the Tacotron first we generate the spectrograms and then uses the web flow model to create waveform from the spectrogram. So I think there's a link to the paper somewhere here, maybe on the site. There's a link to Google blog where it was first published. A nice summary of that. I'll just read this from that paper, from that description. They use a sequence-to-sequence model, map a sequence of letters to a sequence of features that encode the audio. This is an 80-dimensional audio spectrogram. It's a 12.5 millisecond frames, so they capture pronunciation of words and also capture volume, speed, and intonation. So by varying the size of the window there, they will be picking up different features. Now this one needs to run on a GPU as well. So first I'll switch off my other previously running collab, and now I can start again. So collabs have a limit of 1 GPU per user at any time. So if you've got a collab running, it'll prompt you to terminate one of the sessions. I should have. So we start here installing our packages again. It should be pretty good because those, I think most of those shipped with Colab. Now we're going to load a pre-trained model from the PyTorch hub. So just to see where this is. This is where this is published. So these models can be published on GitHub, and you put in a particular file, and then they can be loaded from Torch Hub. There's a description of how this is used, and that's essentially all of this Colab is. So the same commands running in Colab. Okay, so we've loaded that pre-trained model, moving it onto the GPU. This PyTorch Hub has a whole lot of pre-trained models. Just out of interest sake, you can search through these and download them, use them yourself. Lots to play with. Okay, so that's downloaded. We'll do the same with the WaveGlow model. So this is the bit that will generate the audio from the waveform. Sorry, generate the waveform from the spectrogram. that's done. Now we can generate a sentence. And now we use these prepare input sequence utilities. So this will do things like strip out punctuation, etc. And now we chain together the Tuggatron and the wave glow. So at that point, we've got the audio as in the data format. And if we want to listen to it, we can either write that to a file system or we can display it on the screen. Listen to that.
The droll sacraments undertook the spotty opera. The droll sacraments undertook the spotty opera.
Yeah, that sounds pretty good. It's a lot less shaky and shimmery than the previous one. Maybe I'll copy the same sentence. And
The lucrative cooperatives swim the triangular connoisseur.
so that was deep voice. So if I update the text, then I'll redo the utils and the chain. And I can skip this one because I just want to listen to it in the browser.
The lucrative cooperatives swim the triangular connoisseur.
So that sounds to me significantly more natural than the deep voice version. All right, so again, for this one, save that collab, make sure that the code cell output is not being emitted in the change runtime type options. Save copy in your drive, and after you run through, show the output. There's some links down the bottom to more detailed information about that system. We can see we're developing, it's getting more and more natural. So I was hoping to get an ESPNet TDS collab to look at today, but the one that I found wasn't running so well. But if you're interested in your own time, I might, if I can get it to work this afternoon, I'll drop that into the Slack channel. So that's a more recent tech approach. And you'll see that in a couple of years from these systems to that, they are getting the naturalness is becoming quite good. The last activity for the prac is this generating or cloning your voice. So this is again, it's a fairly basic system. It uses a pre-trained model that is then fine-tuned with a very small amount of data. So you can do it with 5 seconds of your own speech. Of course, it'll work better the more you feed it. is a pretty neat system. So the link to the code is there. It's really nice and easy to use. So same sort of approach, we're going to clone the repository and then install the dependencies and install the pre-trained models. And then we'll record or upload some audio of our voice and then synthesize some text based on that adapted audio. Get it going. Here we go. So I'll have to cancel my other session first. This format or the display here in this collab, we see the use of a form in the code cell. So this can be used to hide code. So you might sometimes come across collabs that are in this sort of format. So if I turn all the form hiding on, then I get these interface elements without the code. The code's behind there, so you can press the play button to run the code. Quite a nice way to distribute code tests and such. Click show code to see the core details. So that, again, we get these error messages about versions, but it seems like it will run fine in spite of its incompatibilities. Downloading a pre-trained model and getting that ready for use. Now this gives us an option to either record directly into the browser, in which if you do that, you might be asked for permissions. The browser will want to access your microphone. And so you can do try doing 5 seconds, 10 seconds, 30 seconds, and see if it makes a difference. So put those settings there and then press the play button. And I should get a record button underneath. The dishonest portrayals became the corny rosemary. So there's my 5 seconds of audio. Dishonest portrayals became the corny. No, there's not a real lot of data there for it to work from, but we'll get a sense of it. So we'll either update the text in there or, oh yeah, I've got to use the form. So now it's...
My name is Ben.
Ah, that sounds more like JT than me, but that's not too bad for 5 seconds. So maybe try doing that with like 20 seconds of audio and see if it makes a difference for you. And if anybody feels like sharing either the audio file or your observations of accuracy, that'd be cool. I'm going to record 20 seconds now and see if that makes much of a difference. The small pup gnawed a hole in the sock. The fish twisted and turned on the bent hook. The swan dive was far short of perfect. The beauty of the view stunned the young boy. 2 blue fish swam in the tank. Her purse was full of useless trash. The colt reared and threw the tall rider. The small pup gnawed a hole in the sock. The fish twisted and turned on the bent hook. The swan dive was far short of perfect. Notice I'm getting some microphone hum on that as well, so that might affect the learning.
My name is Ben.
So it seems to have learned a lot more of the intonation from the longer sentence readings, and it would also be worth training on those Harvard sentences, which are much more natural English and semantically correct, understandable sentence structures compared with the NIT or the sus ones, because the semantically correct ones might give it a more natural intonation. I'm going to try changing the sentence. Let's see what it sounds like.
Smoky fires lack flame and heat.
That's probably not going to validate against my bank's voice print, but it's an interesting process to go through.